Hello everyone, my name is Colin Christie, and here I will be presenting my work on random forest classifications for ASAS-SN light curves. The All-Sky Automated Survey for Supernova, also known as ASAS-SN, is a wide-field photometric survey that monitors the entire night sky every night. In recent years, ASAS-SN has discovered millions of variable candidates, far too many to be classified by hand. For this project, I aim to correctly classify variable stars found in the ASAS-SN G-band dataset based on their folded light curves. For periodic variables, one can fold years' worth of observations based on their pulsation periods to create a recognizable image. From these images, I will train a random forest classifier to correctly distinguish between variable types. Before I trained such a classifier, I first had to prep the data of the training sample. The first step was to plot a visible light curve from the photometric measurements. Then I converted these plots to a PNG file that could later be translated into a NumPy array where it could eventually be appended to a pandas data frame, much like the MNIST dataset. I trained the random forest classifier to identify roughly 8,700 light curves for the 6 variable types shown here. For my initial test, I constructed the model to have 100 estimators, a max depth of 10, and use the Gini coefficient to measure the quality of each split. For the initial test, the overall accuracy was found to be roughly 80%. This isn't great, but it's a step in the right direction. To further analyze the results, we can look at the confusion matrix of the model's classifications. As you can see, it appears that the model only predicts stars as EA, EW, and RAB variables. This is likely due to the overrepresentation of these variables in the training data, causing our model to overclassify their types. To combat this sampling issue, we can consider the underrepresented variables, Cepheids, Miras, semi-regular variables, as being in a class called pulsators, along with the R-Lyrae variables. Doing this improves accuracy to roughly 90%, which is a big improvement from the first test. To optimize our model further, we can analyze how the error in our model changes with complexity. As you can see, the error seems to level off at around a max depth of 10, so we can adjust our model parameters to include this metric. Doing this increases the accuracy to about 95%, meaning that the classifier can now accurately distinguish broad variable types from one another. To make this model more applicative to a wider spread of variable classifications, another type of model must be employed. This is because in practice there are hundreds of variable types, meaning that one would not be able to use image classification alone, as you would have to consider other factors including the pulsation amplitude, period, etc. However, this algorithm may be useful for funneling a large data set of stars into their broad variable types, at which point a more refined model could stratify each type into higher order classifications. Thank you.